So what I want to talk about in this lecture is similar to some of the concepts that we've talked about with polynomials. One thing we're going to talk about is we don't usually call it this when we're talking about rational expressions, but essentially it's end behavior, right? You remember when we were talking about polynomials, the end behavior was how the graph behaved, or how the function behaved, when the x values got either really big or really small, right? We're going to do something similar with rational functions here. And we're also going to look a little deeper at what's going on, again, kind of focusing on what the graph is doing when we get in a neighborhood of values where the function is undefined. All right, so first, just make sure we're all on the same page. I've got the definition here. A rational expression is an expression that has the form p over q, where p and q are polynomials. So essentially, it's one polynomial divided by another. All right, the way I want to approach... So let's start our investigation with this example here. Kind of the most basic rational function you can get, right? It's just 1 divided by x. And hopefully, you all recall, this is undefined when x equals 0. You can't divide by 0. The denominator is 0 when x equals 0. So what I want to do here, I say approach this experimentally. We're really going to kind of go back to basics. When in doubt, and you're trying to graph a function, plot points. Right, so let's calculate some x values that are close to 0. Right, you see that's what's happening here. Every step I get a little closer to 0. And let's see what the function does. All right, so f of 1 is 1. F of 0.1 is 1 divided by 0.1, which is 10. F of 0.01 is 1 divided by 0.01, which is 100. All right, so you're starting to see what's happening, right? But before we do the last one, these numbers are not just getting bigger, they're getting a lot bigger, and they're doing it pretty quickly. All right, so let's do the last one here. F of 0.001 is 1 over 0.01, which is 1,000. Okay, well, let's graph this stuff, right? I've got these are just my points over here on the left. Right? Those are the numbers we calculated. And if I try to graph these, what happens? Well, I run into trouble really fast because the numbers get big. When x is equal to 1, y is equal to 1. When x is equal to 1/10, f of x is 10. That's already up off of my graph. When x is 0.00, now it's off the whole page. And hopefully now you see the trend, right? The numbers are getting really, really big. But the key point I want you to see here, doesn't matter how close I let my x values creep into 0, the function value itself is never going to be 0. I'm never going to actually make it all the way to the y-axis and have a y-intercept. Okay, so this graph in this section looks like this. And the way we indicate that the function is going to get close and closer to 0 without ever actually getting there is with a dashed line. Right, so I'm going to draw a dashed line here all the way up. Sorry, I meant to grab a darker color. There we go. That's better. There and there. And this line that the graph approaches but never actually touches, it has a name. It's called an asymptote. Spelled a little strange. It's got a P slipped in there. Okay, so the way I would describe this, asymptotes are lines. You see that in the picture. So if you're asked what is the asymptote of a function, your answer is going to be the equation of a line. Right? So in this case, I would say this function has, let me write it, f of x has a vertical asymptote at x equals 0. Right? That's how we would phrase it. Okay, now there's an obvious kind of next question here. What about the other side? What's happening on the left side of 0? Well, if you come up here, we've already got these points to work with, right? If you come up here and you make all of these points negative, make x -1, -0.1, -0.01, and so on, what's that do to the functional values? Well, it just reverses their sign as well. Okay, so what's happening on the left-hand side is kind of the mirror image, right? It starts here at -1, -1, and then drops off and becomes negative really quickly. So that's the behavior on the left-hand side. Okay. So now, let me ask you this. Right? Let's go the other way. Now, let's talk about end behavior. Let's talk about the end behavior of the function. And you remember, when we refer to end behavior, what I'm asking is, what is the function doing? What is the graph of the function doing as x values get really, really big, or really, really small, off in the negative direction? Well, the plotting points method worked pretty well for us on the last one. So let's try it again. Right? Let's put these numbers in and see what happens. But when I put 10 in, f of 10 is 1 over 10, that's 0.1. F of 100 is 1 over 100, that's 0.01. Okay, and you can continue this, right? You can actually go to your calculator and evaluate these if you really want to see it. F of 1,000 is 0.001. F of 10,000 is 0.0001. Okay, hopefully you see we have a very similar behavior happening here. Instead of getting really, really close to the y-axis and never touching it, now the numbers are getting smaller and smaller. They're getting closer and closer to 0 as the x values get big, but they're never actually going to make it there, right? There is no number that when you put it in there for x, f of x is actually going to be 0. The graph does not actually have an x-intercept. Okay, so if I graph this, I'm going to get graph paper here. And I'm going to have to fudge my scale a little bit of it because even 10 is already off the graph on the right-hand side, right? So just kind of work with me on the scale. What we're seeing here is that it starts at 0.1, drops down, and keeps dropping, right? It gets closer and closer to the x-axis, but never actually gets there. Again, that's our asymptote behavior, right? And I'm going to indicate it the same way. I'm going to draw a dashed line here, and I'll put it on the other side too. We'll look at the negative behavior in a second. And there's my asymptote. And I would describe this exactly the same way. I would say f of x has in this case, a horizontal asymptote at y equals 0. All right, and again, what about the negative side? Right, what's happening when we put in really big negative numbers? It's the exact same behavior. If I switch all of these x's and make them negative, the y's become negative, and you see the exact same behavior duplicated on the left side, only now the y values are negative, so we're below the x-axis. So it's going to be here and creep up from below. Okay, now let's combine this, right? Let me bring in that vertical asymptote that we saw, right? The vertical asymptote was here. So if I fill in that part of the graph, it drops off here and goes up here. And that's what the graph of this function looks like, right? It has two asymptotes, one vertical and one horizontal. Okay, so that's good. Now, hopefully you have an idea what I mean by a vertical asymptote, what I mean by a horizontal asymptote. So the next thing we need to consider is how can we generalize this, right? If I give you some arbitrary or random rational function, how can you tell me where the asymptotes are? Okay, well let's take a look at this thing, right? This is very, very similar to our original one, and I need you to kind of think back to your maybe college algebra course, right? What is the difference visually between f of x, no, maybe don't use, I already used f over here, right? Let's call it something else. G of x equals 1 over x, and f of x equals 1 over x plus 1. Well, hopefully you remember right from your discussion of transformations. F of x is g of x translated 1 unit to the left. Okay, so if I take that whole 1 over x graph, asymptotes and all, and shift the whole thing 1 unit to the left. Now the vertical asymptote isn't going to change. The horizontal asymptote isn't going to change. Right? It's going to stay right where it is. The vertical asymptote, on the other hand, that gets pushed sideways. It's going to become this. Now let me fit the graph in here. It starts off at the asymptote up here, drops down, and goes off to the other one. And does the same thing on the other side here. It starts and then drops down. Okay, so there's my graph, and we can see visually that the vertical asymptote is now at x equals -1. Okay, compare these to the functions. The original function had a vertical asymptote at x equals 0, and it was undefined at x equals 0. Now the horizontal, my f of x graph, on the other hand, has an asymptote at x equals -1. And remember how we find where it's undefined? You take the denominator, set it equal to 0, and solve that equation. We get x equals -1. That's going to be our method. That's going to be our method for finding vertical asymptotes. Let me write it out here. A rational expression has a vertical asymptote wherever, can't spell today, where the denominator is equal to 0. And I want to emphasize this here. There's a big caveat, right? Before you try to make this determination, simplify first. It's not just the points where the function is undefined, right? It's the points where the simplified denominator is equal to 0, right? That's gonna be our method. Okay, so that's vertical asymptotes. So that was, sorry, we discussed the rule. I got a little ahead of myself. How about horizontal? Horizontal ones, the situation is a little more complicated. Okay, so what I've done here is I've got 3 different rational expressions. And I want to apply my same method. I want to plot some points, see what's going to happen. Okay, now I'm not going to make you sit here while I crank out 12 different functional values. But I've got them all on the next screen. I want you to pause the presentation, see if you can't calculate a few of these. Right? For example, f of 10 would be 3 divided by 10 plus 1, which is 3/11ths. And we're graphing, so then you're going to want to go to your calculator and get decimals. Right? So go ahead, if you like, you can pause, work some of these out. See if you can spot the trend for yourself, right, before you go to the next slide and see my results. All right, so these are the numbers I came up with, right? And I want to look at all 3 of these 3 cases and look for a pattern. Right? And then we'll see if we can generalize that and come up with a rule. Okay, so on this one, what's happening? The functional values are getting smaller and smaller and smaller. They're getting closer and closer to 0. Right, now over here on this one, they're not getting smaller, but they are kind of settling down. 2.9 is close to 3, kind of close. 2.99 is closer to 3. 2.999 is even closer. 2.49. The trend here is that these function values are getting closer and closer to 3 every time we go further out on the x-axis. All right, now what's happening with h? With h, I got nothing. Started off at 27, then we had a jump to 297, then we had a huge jump to 2,997, then another order of magnitude jump. These numbers are not settling down. The way we would kind of phrase this, as I would say, these numbers are going off to infinity. That's how I would describe it. Okay, so how are we going to come up with a rule? Well, the rule for determining a horizontal asymptote is based on comparing the degree of the numerator and the degree of the denominator. And you remember, the degree of a polynomial with one variable, right, all of ours just have x's, is equal to the biggest exponent. All right, so looking at h of x, the degree of the numerator is 2. The degree of the denominator is 1. Over here, with g, the numerator is 1 and the denominator is 1. And then finally with f, the denominator is, of course, still 1. They were all the same. And the numerator is 0. Okay, comparing these degrees is where our pattern is going to be. Okay, if the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. Right, now over here, I've got it the other way around. Here the degree of the numerator is less than the degree of the denominator. In this case, it's always going to be the same. The horizontal asymptote is going to be y equals 0. It's the x-axis, right? And finally, this is kind of the it's not hard to do, it's just hard to write out in words. When the degree of the numerator is equal to the degree of the denominator, then there is a horizontal asymptote, and it's at y equals, see, it's hard to write this out. It's the numerator's leading coefficient divided by the denominator's leading coefficient. Leading coefficient, that's just the number in front of the biggest term, right? So looking at my example here, the leading coefficient of the numerator is 3. The leading coefficient of the denominator is 1. And yeah, that's exactly what we saw. If I do 3 divided by 1, that's just 3. Right? So this is going to be our method. Right? This is how we're going to determine the horizontal asymptote of a rational function. So let's look at some examples. All right? I want to know, what are the asymptotes of this function? Okay, the horizontal ones are usually the easiest. The degree of the numerator is 2. The degree of the denominator is 2. They're the same. So my horizontal asymptote is going to be y equals the leading coefficient of the numerator, that's 1, and the leading coefficient of the denominator, that's also 1. So this function has a horizontal asymptote at y equals 1. Okay, now to get To get the vertical asymptotes, step number one, simplify. Right, step number one is simplify this thing. So let's factor everything, see if I can cancel some stuff. F of x is x plus 2 times x minus 1 over x plus 3 times x plus 1. Okay, nothing cancels, right? There were no factors in common in the numerator and denominator. Nothing cancels out. So my vertical asymptotes occur where x plus 3 equals 0. That's x equals negative 3. And where x plus 1 equals 0. That's where x equals negative 1. Those are my two vertical asymptotes. X equals negative 3 and negative 1. And that's it. Right? That's all we have to do to find these things. Okay. So how about this guy? Right? How about this guy? Let's see what we come up with here. First, let's do, again, because it's usually the easier of the two, quicker anyway, the horizontal asymptote. The degree of the numerator is 1. The degree of the denominator is 2. The denominator is bigger. Anytime the denominator is bigger, the horizontal asymptote is y equals 0. All right, so excellent. Vertical. Right, how about the vertical asymptote? Let's see, what do we get here? Simplify, right? F of x is x plus 2 over x plus 5 times x plus 2. Okay, so now I got some stuff that cancels. That x plus 2 goes away, and this is 1 over x plus 5. So this graph only has one vertical asymptote. It occurs where x plus 5 equals 0. That is x equals negative 5. Just one. Okay, so you might reasonably thinking, right, asking the question, what happens to the graph at x equals negative 2, right, at that other point where it's undefined? That's an excellent question. We're going to, and just to give you a quick little foreshadowing, there's going to be a hole in the graph at that point, right? And we'll talk more about that in the next lecture, where we start to bring all of these things together. These things about asymptotes, things we already know about, intercepts, for example, and look at how to actually sketch the graphs of some horizontal function, of some rational functions. Okay, so let me give you one here. Take a look at this. Try coming up with both kinds of asymptotes. All right, so let's see. Let's do the horizontal first. The degree of the numerator is 2. The degree of the denominator is 2. So the horizontal asymptote occurs at the ratio of the leading coefficients. That's negative 2 divided by 1, which is negative 2. All right, so now I got to think about, let me clean up a little here so I can see my function again. Now I got to think about vertical ones. And to find vertical ones, we need to simplify this. So let's do some factoring. F of x is equal to negative 2x times x minus 1 over x minus 6 times x minus 1. Yeah, good. We get some canceling action there. So this function has a vertical asymptote where x minus 6 equals 0, which is x equals 6. One of each. Okay. So let's stop and think for just a minute about some possibilities. We've seen functions that have one vertical asymptote. We've seen functions that have two. The number of vertical asymptotes is practically unlimited. As many factors as you can cram into the denominator of your rational function, that's how many vertical asymptotes you could potentially have. Horizontal asymptotes, those are different. A rational expression can only have at most one horizontal asymptote. We've seen a situation where it had none, right? That is a possibility. A rational expression cannot have two or more. It is possible for a function to have two or more. There are functions that have more than one vertical asymptote, but not rational functions. Okay, our rational functions are going to have either 0 or 1. So where do we go from here? In the next lecture in this series, I'm going to do what I hinted at on the previous slide, or the second slide back. We're going to look at some examples where we're actually going to graph rational functions. We're going to take all of these bits and pieces we've talked about, where the function's undefined, where both kinds of asymptotes are, where its intercepts are, and put all of that together and see how we can start to sketch some pretty accurate graphs of rational functions.